Right. Okay. Sorry about this. Uh, Last week there's a very important topic we talked. That was the measurement to get the answer of the compressibility factor, right? So basically, we will have I will give you either two of these, two of the pressure, temperature, or volume, so that you will get two of these PR or TR or PR or VR or TR or VR. So you can get these two. Uh, so and then use this chart to find the compressibility factor. So when you get a compressibility factor, you get this compressibility factor back to this uh, equation of state. So you know Z, and if I already gave you pressure and volume, so you will be able to get temperature. Or if I give you temperature or volume, you will be able to get pressure, for example, like this. So this is a very important flow chart for you to know how to find out the relationship between pressure, temperature, and the volume for an ideal gas. Okay? So I want you to know this because this is important and this will be in your final exam paper. So, okay, so it's important. I want you to know. So today we are going to talk about a non-ideal gas mixture. So last week we only talked about single gas system. So now we have a mixture gas. So for the single, let's go back to the last week. Single component, we have single component for non-ideal gas, and we already introduced you some equations, right? I hope you remember various equation of state. Okay, and we also introduced truncative various equation of state. I hope you remember. And after that, we talk about cubic equation of state. That means that cubic equation means that we will have a value cubic power of 3, right? As a kind of cubic function or cubic equation. So we introduced two equations. The first one is called van der Waals equation of state, which is showing this like this. As you know, this is value power 3, right, in this equation. And another equation is SRK equation of state. So what you need to know is the definition of the temperature and V over carat, right? Specific molar volume and pressure. And this A and B are the parameters. So I will give you the equations. I will give you the equations related to the A and B parameters. Okay, and this one they have another one which is called alpha. Okay. So as long as you have this equation and I give you the parameters, so I just want you to find out the relationship between pressure, volume, and temperature for a single component, which is for non-ideal gases. And also we will also introduce you the compressibility factor equation of state, right? PV equal to Z MRT, right? Right, NRT, sorry, PV equal to Z NRT. So this is a compressibility chart. And you need to find out Z here. So how about the multi-components? There are two things we want to introduce you here. One is mixture rules, one is case rule. Actually, mixed rule is more complicated, so we just introduce you the case rule only. The case rule is to use generalized compressibility chart. Okay, so this is case rule. Assume we have three types of the gases in the chamber. They are A, B, and C. So A species has its own critical temperature and critical pressure, right? B species has its own has critical temperature and pressure, the same as C. So and we want to know the pseudo properties. If I ask you what's the critical temperature and critical pressure in this system for these three gases, can you tell me how do you do this? We call TC prime. So it looks like a kind of summation of this, the property of this mixture, right? Okay, so the definition of TC prime, PC, and also I want to know that is any reduced temperature and pressure in this system. Of course, these are all pseudo. Pseudo means that it's not real, but we use this TC prime, PC prime, and TR prime, PR prime for the calculation only. Okay, for the calculation only. So if we have TC prime, PC prime, and if we have TR prime and PR prime, we probably can use compressibility factor to find out compressibility. We probably can be able to use compressibility chart to find out the compressibility factor, Zm. Okay, M stands for mixture. Right, so how can we do that? So for gas mixture, PV equal to Zm nRT. Okay, this M is a mixture. So let me show you how to do it. Okay, so assume there are three types of gases in this chamber. And then pseudo temperature, we use TC prime to represent pseudo critical temperature. And that will be, for the TC prime, that will be equal to YA times TCA plus YB times TCB plus YC times TCC. Or if you have the number 4, you have the number 4 gas that you plus YD times TCD, right? Okay, etc. So assume we have 3 types of gases in this chamber only. So this is like this. So what's YA, YB, YC? YA, YB, YC are the molar fraction. So you need to know the proportion of A in this chamber, proportion of B in this chamber, and C in this chamber. So that will be easier for you to use this to get the TC prime, which is what we call pseudo-critical temperature. If I say this to you, I'm sure you immediately understand what is pseudo-critical pressure. Pseudo-critical pressure is TC prime. TC prime is equal to YA times PCA plus YB times PCB plus YC times PCC and plus etc. Right? So in your final exam paper, I don't show you this. You need to know how to calculate TC prime and PC prime. Okay? Easy. If I give you the molar fraction of the A, B, and C. So how about pseudo-reduced pressure and temperature for a mixture gas, or for a gas mixture, So assume the temperature and pressure in this system is a capital T and capital P here. So the system temperature pressure is T and P. Okay? So for a pseudo-reduced temperature will be TR prime equal to T divided by TC prime C. We already told how to do TC prime, right, in the previous slide. So TC prime will be like this. So once you get TC prime, you can get TR prime. Right? So this is we call it pseudo-reduced temperature. How about pseudo-reduced pressure? The same. PR prime equal to P divided by PC prime. So now you know the pseudo-reduced temperature and pressure. So we combine these two together. How can we get compressibility factors from the pseudo-reduced temperature and pressure, or the pseudo-reduced volume? Okay, so compressibility factor for a gas mixture, Zm, can be obtained from a compressibility chart. So this is what we call compressibility chart. And compressibility factor is here. So again, you can use PR, VR ideal, and TR to get the Z. Of course, this figure is for uh, single gas, but it also can use for a gas mixture. Okay, so it's the same chart. So first of all, you need to know where is TR from. TR from is this one. Again, TR from, right? This is solid line here, from 5, 3, 2, 1.6, 1.4, 1.3, 1.2. This is solid line here. And PR prime is this one. It's x-axis from 0, 1, 0 0.1, 2, 3, 4, 5, 6, 7, 8, something like this. And again, we have VR ideal prime. Okay, so it's this is the equation you need to know. So remember, I don't show you this equation in your final exam. You need to remember this. So it's here. So this is exactly what you learned last week, where to get the PR, VR ideal, and TR. And now it just changed to PR prime, TR prime, and VR ideal prime. That's it. Using the same figures, same chart. Okay? We are going to do a practice example very soon. Okay? So let you have so you just know how to do it. So a gas mixture will be P V over Kara equal to Z M. M stands for mixture, right? Okay. R, gas constant and temperature. Right. So what's case rule? Case rule is that the case rule is a kind of approximate volume only. It's not the exact value. Okay, it's not exact value. And then case rule normally is used in the non-polar compounds. So A, B, C, D normally is not a kind of polar compound. It's they are non-polar compounds. And especially every compound has its own TC and PC, and TC and PC between each other is less than 2. Okay, the ratio is less than 2. Okay, this is general rules. Right. But so another rules to use for a gas mixture is called mixture rule. It's more complex, but more accurate. We don't have time to introduce this in this lecture, so we just introduce you case rule only. Right. So let's do the practice. 5.4-3 case rules. So, for example, if I give an example like this, 75% hydrogen and 25% nitrogen is a molar basis. So you can use the fraction, right? So hydrogen is about hydrogen is 3/4, right? Nitrogen is 1/4. Okay. So it's contained in a tank at 800 atm at minus 70 Celsius. Well, under this condition, 800 atm minus 70, you immediately realize you cannot use ideal gas equation of state to find out your answer. Why? Pressure is too high, temperature is too low. So it's not the case of ideal gas, right? Okay, so you have pressure, you have temperature. Of course, what you want to know is what? Volume, right? What you want to know is volume. So estimate the specific value of the mixture in liter per mole using case rule. Okay, can you get this answer? In your final exam, I might change the ratio here or I might change something. So you need to practice this example. Right, so let's do it. So let's go to step 1. The solution, step 1 is what? You need to find critical temperature and critical pressure of the nitrogen and hydrogen, right? First, of course. This is important. And then what happened? Next one, does they follow Newton's correction? You know, Newton's correction, you need to remember, only apply for a very small size of the gases, like hydrogen or helium. Okay, so is any helium or nitrogen in this chamber? Yes, hydrogen, right? So you need to do a Newton correction for the hydrogen. So you had to plus 8 numbers, 8 Kelvin and 8 atm for the hydrogen in the TC and in the TC and PC. So once you find out TC and PC, you need to add 8 volumes, right? Value. Okay, you need to add 8 in this value. Okay. So after that, you need to find out the pseudo-critical constants for hydrogen and helium. We use TC prong and PC prong, and I already introduced how do you find out, right? Using molar fraction. So once you find out TC prong and PC prong, actually next you need to find out TR prong and PR prong. And this is the equation you need to know, right? Okay. And then what happened? If you have TR prong and PR prong, you go to this PR and TR, you find out ZM. You find out a Z mixture compressibility factor, right? So you obtain from the figures 5.4-4 and the PR prong and TR prong. So let's do it. So for the case rule, you need to do the calculation by yourself, okay? So in the end, I tell you what's the answer of TR prong and PR prong. So the answer of TR prong and PR prong is here. In the example 5.4-3, TR prong is 3.26, PR prong is 33.3. So you need to use this chart. So tell me the answer of the ZM. Where is this? So TR prong, TR is here, right? So it's 3.26. You have 1, and you go to 2, 2.5, 3.00 to 3.5. So it's somewhere between 2.5 to 3.00, right? So it's somewhere the solid line between these two solid lines. Okay? And how about PR prong? 33.3. 33.3 is somewhere here. 31, 32, 33, 33.3. So it's somewhere here. Right? So you have this line here. So use your ruler. You know, you have ruler. And you know it's somewhere here. And then you go to this part. So you probably draw a solid line between 3.000 and the 3.5. So you draw a solid line between this and you get somewhere here. Right? And then what happened? Go to this side. Somewhere in this point. So that will be, this is 1.0, 1.2, 1.4, 1.6, 1.8. So between 1.8 to 2, right? In your final exam, if you tell me this is 1.8, that's not correct. If you tell me it's 1.82, wow, I might give you scores. If you say this is 2.0, no, you are wrong. So the true answer is 1.86. So if you tell me between 1.82 to 1.88 or 1.9, wow, that's okay. Because we know case rule is kind of approximate value, right? Approximate value. It's not exact value. So once you know ZM is equal to 1.86, so you use PV equal to ZM RT. So you can get what? You can get the volume, right? Volume in this case. Okay? So I don't want to waste your time to do the calculation. Please go home and do the calculation by yourself. This is important. I want to tell you again. I don't want to fail you. If you do the practice, you can get the points in your final exam. Okay, so let me summarize the 5.4C, a mixture gas. So once you have three, for example, you might have three mixtures, or you have three gases in the mixture. You might have two. In the previous case, it's two, right? So you might have four. But anyway, we are doing in the same thing. So for example, we have three gases in a mixture. And then, first of all, you need to find out critical temperature and critical pressure for these three. Okay, in the table. In your final exam, I will give you the table. I don't directly give you the number. You need to find out by yourself. Okay, and then after that, you need to know the molar ratio of this 1, 2, 3. I might give you the weight ratio, and you convert it to molar ratio, for example, something like this. Okay, and then after that, you need to know, do they follow the Newton's collection? For example, is any hydrogen or helium gas in a container, in a chamber? If yes, you need to do Newton collection. Next, once you have critical temperature and critical pressure for three species, then you need to find out the pseudo-critical constants. The first one is pseudo-critical temperature and pseudo-critical pressure, right? And after that, what do you need? According to this, if you have pseudo-critical temperature and pressure, and you have temperature, really temperature and pressure, what do you need? You need to get pseudo-reduced constants, right? It can be TR Planck, PR Planck, or VR ideal Planck. Okay, and after that, once we know two out of these three constants, okay, we can use compressibility chart to find out what? To find out Zm, which is compressibility factor for a gas mixture. Okay? And after that, once you have compressibility factor, in the previous case, 1.86, right? So you put the Zm back to this compressibility equation, PV over Kra equal to ZmRT, you can get the answer of volume or pressure or temperature. This is the summary of the case rule for you to find out the relationship between volume, pressure, and temperature. Okay? Ladies and gentlemen, important. Remember that. Right. So, this is a summary of chapter 5. After that, we're going to move to chapter 6. The chapter 5 tells us just one phase. It can be solid, it can be liquid, it can be gas. And we talk about gas, we talk about liquid and solid very fast. Normally, we're dealing with density, right? Density. Okay? But solid is, gas is a little bit complicated. So we mainly focus on gas phase in chapter 5. And so we divide it into two parts. One is ideal, one is non-ideal. And one is single gas, and one is multi-component, or a gas mixture. Right? So for an ideal gas, single gas, for a single gas, ideal gas, so we use PV equal to nRT, ideal gas equational state. This is no problem. Okay, how about multi-components? We use Dalton's law and Amage's law to tell you how to dealing with the multi-component ideal gas equational state, right? So this is P, this is what? Dalton's law, this is Amage's law. How about non-ideal gas equational state? Non-ideal, for the single gas, we use, again, variable equational state and the cubic equational state and the compressibility factor equation. Okay, for the multi-components, non-ideal will be case rule only. We only introduce you this. Of course, there's a mixture rule, but we don't introduce you here. Okay. Right. Right. Okay. This is called fire piston. What is fire piston? If all the gas follow ideal gas equilibrium state, there's no this kind of fire piston. Because of what? Fire piston is the one which you have a piston and you put a flammable materials in this fire piston, and you push this piston very, very hard, very, very fast, and you see the fire come out. And because gas collide to each other and generate a very high temperature can reach to more than 200 Celsius. This ignite the fire come out. Okay, and then that's why you get something burned in the piston. So when you have a barbecue or when you go to camp in a very in the forest, you can use this tool to get the fire. Of course, now you don't use this. Anyway, so what I want to say to you is this: if you follow ideal gas equilibrium state, this never happened. Right. Today we move to the chapter 6. It's getting excited for me because this is really chemical engineering. Like the chapter 4, chapter 4 is very basic knowledge you need to digest, you need to know, but that's common sense. But chapter 5 is very easy actually, and chapter 6 is very fun because you need to use your imagination to think of the multi-phase system. It can be generally is liquid and gas. There are two phases. It can be only one single component, or it can be components. So you know you can draw a chart like this: one system, two system, and then one component, multi-component. It's fun. It's fun. So I'm getting excited. How about you? You're getting excited, right? To learn something new. Okay. So first of all, let's talk from something fundamental: solid, liquid, and gas. Okay. So you think of water, and then we have phase change operation. This is water. You have ice. You have liquid water. You have vapor or steam or gas, right? So if the water go to ice, what's the term? What's the English you need to use? From liquid to solid. Freezing, right? You freeze, right? What happens if you have solid to liquid? Melting, right? Melting, you melt, melting. How about liquid to gas? Evaporation, right? How about gas to liquid? Condensation. How about solid to gas? Sublimation, right? Sublimation. Okay, so how about gas to solid? Deposition, deposition. So these terms is telling you that once you have phase change, you need to use these terms to describe what's going on. For example, if you use deposition, you understand it's come from solid phase to become liquid phase, gas phase to become solid phase. That's why we call deposition. For example, chemical vapor deposition. So you have a chemical species in the vapor phase, and you deposit on the solid. So we call chemical vapor deposition. We use CVD for short. This is a very common process in the semiconductor industry. Okay, so you have one species, and you do the phase change operation. And how about separation and purification? If you have two species instead of one, and you want to separate these two species by phase change operation. Okay, that will be remain A in the origin phase, and most of B transferred to second phase. We learned this when you study in chapter 4, right? Like distillation. If you have mixture of the if you have mixture of the two liquids and use distillation to separate species A and species B by what? By the differences of their boiling point, right? Okay, so this is what we call separation of purification. How about the separation of nitrogen and oxygen? You can liquefy one of these type of gas, right? You can liquefy oxygen or nitrogen. Okay. So this might be easier for you to understand the gas transition, phase transition. So from solid to liquid, you melting, right? From liquid to solid, freezing. From liquid to gas, evaporation or vaporization. Okay, this is if you use SA, this is the English term. It's not American, right? Condensation, you can use Z or S. S is English, Z is American. Okay, and then for this is sublimation or deposition. Of course, you have a triple point here. So let's talk about the separation or purification process. The first one is called leaching. Leaching is what? The definition of leaching is that you have something in the solid phase and you want to take the something away from the solid phase and make it become in the liquid phase. This is what we call leaching. One of the most important, or one of the well-known process, leaching process is what? The coffee. You make coffee by this process. So the operation of dissolving a component of a solid phase in the liquid solvent. So this is the coffee powder, and you put hot water into this coffee powder, you'll come out with a nice coffee, right? So the coffee come out from the coffee bean, okay, together. So hot water plus ground coffee bean, you got a nice coffee. This is called what we call leaching. So solid phase to the liquid phase. And second process, next process is called scrubbing. Scrubbing. What is scrubbing? You know, when you go to night market, and then you see a barbecue there, and it produces a lot of smoke. So if you produce a lot of smoke, you don't want to let it come out because you got air pollution. So you need to use water to let the smoke. You need to eliminate the smoke by water. So this is what we call scrubbing or absorption. Ladies and gentlemen, absorption in Chinese, 吸收. What is absorption? The process in which a gas mixture contact in a liquid solvent and a component or components of a gas or gases dissolving in liquid. So now if you go to night market and then you pass through a vendor which has a barbecue, they're selling barbecue, and then they always have a machine which suck all the smoke away and put it to a tank and come out with a tank with no smoke. Might be not a scrubber. It can be a what's that? Activated carbon. That's absorption. That's a desorption. 吸附. Okay, I'm going to tell you very soon. This is one of important. This is very well-known process, scrubbing. So you have a gas come up from the bottom and go up, and you have shower. The gas will go to a shower, water shower. So water will absorb something in the gas phase and then make it absorbed in the water and come down like this. So you come out with clean water, clean air from this part. So scrubbing is an absorption current designed to remove undesired components from a gas stream. Okay, this is one of the famous example. First, in the film, you know, when you do the combustion with charcoal, with coal, and you burn the engine, and because the coal contains some of the sulfur compounds, and the sulfur will become sulfur dioxide. Okay, and then if sulfur dioxide meet with air, and then they will become SO3, and SO3 with water will become S2SO4, and this is what we call is acid rain, right? So you don't want to you don't want to produce this, so you better make SO2 dissolve in the water first before you release the air come out, right? The air. So that's why you need to use this scrubbing, we call scrubber. Sometimes scrubber, SCRIBBER. Okay, let me say this again. You introduce the the water with particles or smoke from the bottom, and then this stream will go under the shower of the water, and water absorb the particles or smoke, and then condense in this bottom, and the clean air will come out from the top. Okay, next one is called distillation. I'm sure you already know distillation, right? So distillation is the process of the separation components substance from a liquid mixture through vaporization and the condensation based on different volatility. Okay, volatility. Okay, or it can melting point, boiling point, right? Vaporization points and the components in the mixtures. Distillation is a unit operation and or a physical separation process and a non-chemical reaction. So distillation is from liquid phase to gas phase, right? And then the gas phase condense here. So you separate A and B, right? You have mixture of A and B here, and you have A come out, it become vapor and condense here and drop in this tank. So this is vaporization and condensation process. And for example, methanol in the water, so you can, because of different vapor pressure, you can separate methanol and water. This is one of the example. Okay, next one is separation process is called liquid extraction. I'm sure you won't forget this liquid extraction because this was in your midterm exam, right? MIBK and acetone and water. So acetone and water like each other, but MIBK take away acetone, take away acetone from water, right? So MIBK and acetone was doing the distillation. So a process in which a liquid mixture of two species. There's two mixture of species. One is solute, one is called feed carrier. Is contact with a mixer with a third liquid, which we call solvent. That is miscible or nearly immiscible with the feed carrier. When liquids are contact, solute transfer from the feed carriers to the solvent. The combined mixtures is then allowed to settle into two phases that are then separated by gravity or a decenter. Okay, and I hope you remember we already used this water, acetone, and MIBK as an example for you. Here we give you another example. So we have feed carrier, solute, and solvent. So solvent takes solute away, leave the carrier alone. Okay, so this is what we call liquid extraction. So here's another example: a separation of paraffinic and the aromatic hydrocarbon. This is called paraffinic hydrocarbon. This is called aromatic hydrocarbon. So they have very similar chemical compounds. There are 6 carbons. 1, 2, 3, 4. There are 5 carbons, right? And there are 6 carbons. Yeah, very similar. And then if we use glycol, this one we call EG. We put this EG into this mixture, and this aromatic will be taken away from the feed carrier, from the aromatic hydrocarbons. So this is what we call liquid extraction. And we do the distillation to separate these two, right? Okay, we can use. Okay? Okay, the next process is called adsorption. Adsorption. So adsorption is that we separate the species from the gas or liquid phase and make it condense to a solid phase. This is what we call adsorption. The differences between adsorption and absorption is adsorption is 吸收, sorry, absorption is 吸收, adsorption is what? 吸附. They are from different phases. So process in which a gas or liquid mixture contacts a solid, and the mixture components adhere to a surface of the solid. So why is this? So the separation of the, this is one of the examples, the separation of the isomeric mixtures, these three. Okay, if a mixture of these three, you can use adsorption to separate this. For example, if you have a molecular sieve, if you have a sieve, if a mesh, and these two can be passed through the mesh, the sieve, but this one will stay on the top. Okay, so this is this pore is not big enough to this stay, and these two can pass. So this is called adsorption. I show you one of the important process of the adsorption is called PSA, pressure swing adsorption. So this is activated carbon. Okay, and you know activated carbon has a lot of pores, right? That's what we call activated carbon. And you know, oxygen molecule is smaller than nitrogen, so oxygen will trap into this particle, and nitrogen will be free. So you can separate oxygen from the air by this kind of process, by this adsorption process. So this is activated carbon. Okay, and then why is called pressure swing? Because if we increase the pressure, and this one will be, the more oxygen will be trapped into this particle, and then more nitrogen will come out. So if you put the air into this chamber, and most of the oxygen trapped into this chamber, and then most of the nitrogen come out free. So you have pure nitrogen. And then after you have pure nitrogen, we call desorption. We depressurize. That's pressure, right? And we depressurize. Depressurize, that means what? Oxygen will come out. So you have pure oxygen, pure nitrogen stream, and pure oxygen stream here. And this process is called pressure swing adsorption. So you can easily separate oxygen and nitrogen by this process. Okay, in the past we use liquefy oxygen and nitrogen, right? By very high pressure. This have a lot. You need to spend a lot of money because of you need to use a lot of energy for this. But this kind of process is a good process to separate oxygen and nitrogen. Of course, this belongs to chemical engineering. Okay, the field of chemical engineering. Right. So, and next process is called crystallization. I hope you remember crystallization. We learned this before. So a process in which a liquid solution is cooled or solvent is evaporated to extend that the solid crystal of the solute form. We learned this before, so I just want to get this quick. So next term I want to tell you is it's called saturated or phase equilibrium. Because we use separation process, liquid phase, solid phase, gas phase or liquid phase. Then how about the term called phase equilibrium? That means two phases reach each equilibrium. That means they might have saturated situation. So what's the saturated? Assume if you have a glass of water and you put a salt into this glass of water, and salt will melt, right? So the water will become transparent again. But eventually, if you put more salt into this water, the water cannot digest, or the water cannot dissolve any salt anymore. So you'll come out with solid. So at this point, you realize there's kind of saturation situation. So there's a kind of saturation point. right? It's not a saturation point. And at that time, phase will reach equilibrium because the melt of the sodium, the phase will reach equilibrium because solid phase and liquid phase of the sodium chloride salt will reach equilibrium. Okay, so this is important to you to know, and this is one of the field in the thermodynamics. So when the species transfer from one phase to another, the transfer rate generally decreases with the time until the second phase is saturated. You know, when you put the salt into this water, the dissolving speed will be very fast in the beginning, but very slow in the end, because you know that the second phase, water phase, will reach saturated, with the species holding as much as it can hold at the prevailing process condition. So when the concentration of these all species in which phase no longer change with time, the phases are said to be in phase equilibrium. So this is the two phases, solid and liquid, right? And this is the phases of liquid and gas. So the evaporation rate is equal to condensation rate. That means this reached to the phase equilibrium. Okay, and this place is saturated with oxygen, for example. Okay. Right, and here is a, you know, when we dissolve salt and dissolve sugar in the water, is different mechanism. So the salt is that you take cation and ion away. So you tear salt apart, right? It becomes, the sodium chloride becomes sodium cation and chlorine anion. So you take this apart. But if when you dissolve sugar, it's not the same thing, right? It doesn't become ions, right? You just take the molecule away. You tear molecules away one by one. Okay, so there's different way of the dissolving the sugar and the salt. Right. So let's move to the section 6.1, single component phase equilibrium. Okay, first one is 6.1, phase diagram. What's phase diagram? I'm sure you already know the phase diagram. Phase diagram is one component which is related to the phase, solid phase, liquid phase, or gas phase. And then they are dealing with temperature and pressure, right? Temperature and pressure. And generally, x-axis is temperature, and y-axis is pressure. I hope you remember. Let's make an example of water, phase diagram of water here. So the curve looks like this, and you have a triple point, right? And this go to here, and this go to here. And we know temperature and pressure, and MPB is normal boiling point. This is 1 atm, so this is normal boiling point. MP is melting point, right? Okay. And this is triple point. Triple point means that at this point, the gas, liquid, and solid is coexist. And this is called critical point. Triple point, critical point. And this is above critical temperature, right? This is above critical pressure. And here we call supercritical fluid. Remember? Where's that? And this is gas, right? And below, remember that this is this is critical temperature, right? And the temperature below supercritical temperature is called what? Vapor. Above supercritical temperature is called what? Gas. Remember? Okay. And this part is called supercritical fluids. So there are two separated phases never coexisting. So there's only one phase. There are three phases coexist, right? There's only one phase. And how about this one? This line is two phases. This one, two phases. This one, two phases. This one's three phases. Okay, and this is what we learned before. So when you have this line is vapor liquid equilibrium curve. So if you have a vapor here, this line is vapor and the liquid coexisted. So vapor-liquid equilibrium curve. So there are two phases. If you have, for example, if this point you have this temperature and this pressure, and this will be two phases in this point. So this is called solid vapor equilibrium curve. Solid vapor, right? And this is vapor liquid. So this is what we call what? Solid liquid, right? So this is vapor liquid, this is solid liquid. So once we understand the region and we understand the line, and now the point here is, for example, this G point. G point we can describe, there are two ways to describe G point. The first one is vapor pressure of the substance at temperature T. So you want to know, you want to tell this is called vapor temperature, vapor pressure, especially address the pressure here at temperature T. Or you can address the temperature by pressure. So the boiling point temperature of the substance at pressure P. So you want to address temperature by pressure. Okay? And another point like F here, again, this is melting point, freezing point. Depends, right? At the pressure P. So you just describe temperature using pressure. Or you can use pressure. You want to address pressure by temperature. Okay? Again, H, the same thing. So just want to tell you that how to describe the situation in this phase diagram. Right, so this is a phase diagram of the carbon dioxide. As you know that, you already know the vapor, gas, liquid, and solid. And solid is called dry ice. You know that. Okay, and triple point here, supercritical point here, and the critical point here, and supercritical fluid here. Right. So when you do the comparison of the carbon dioxide, phase diagram of carbon dioxide, this is carbon dioxide, and this is the water, the phase diagram of water. So what's the differences between these two? You know the slope here is positive, slope here is negative, right? Okay, why? Because hydrogen bond. Okay, the freezing point of water decrease with the increasing pressure. Verify this. This is behavior extremely unusual. So normally, most of the species, if you look at their phase diagram, this is normal. Okay, and this is extremely unusual case. So most substances, including carbon dioxide, is the opposite behavior, like this. Okay. Right. Just want to tell you this. You remember. Okay, so the phase transition process I just told you. I don't know whether we have time or not today. This is important. Okay, let me finish this before we stop. So I want to, now you need to use a little bit imagination to think of this process. Okay, this is called hypothetic experiment. Hypothetic experiment. You have water vapor and you have H2O vapor and H2O liquid, and this is the piston. So pure water is placed in a leak-proof evacuated cylinders fitted with a mutable piston. This is a mutable piston, right? Okay. So heat can be added or withdrawn from the cylinder. What does that mean? The temperature can be changed here. Okay, temperature can be adjusted to a desired value. So the absolute pressure of the cylinder contents can be adjusted by varying the force on the piston. So temperature can be changed, piston position can be changed. So the pressure can be changed, right? Because the piston position of piston change, pressure change, temperature change. Temperature can be changed in this piston. So that means what? You are playing with pressure, temperature, and volume. volume. PVT relations. Okay, so this one, this is what the phase diagram of water, right, of the H2O, and we know that we start to imagine from A point to B point, from B point to C point, from C point to D point, from D point to E point. What's going on? Can we describe these points with these conditions? Yes, we can. So let's do it. So phase transition process from A to B. So see that this is temperature to 20 Celsius. And increase to what? Increase to some point like 17.535 millimeter mercury. And what's going on? Two phases. And then increase the temperature again, become what happened? Become 1 atm. Okay, so this is point A, point B. Point B, there are two phases. So point A is vapor phase, like this. A is here, and then point A is here, vapor gas. So imagine if you keep the temperature as a constant and you push the piston slowly. It's not like a fire piston, the video you saw. But this time we don't push it very fast. We push it very, very slow. So you will see something condensed. You will see water condensed. So this is called condensation at point B. When the temperature, the pressure reaches to 17.535, the first drop of the water will come out. So this is called condensation at the point B. At this moment, you have water, liquid water, and the H2O vapor and H2O liquid. Okay? And once you push harder and harder, pressure doesn't change, but more liquid come out. So your pressure will keep a constant. Temperature keep a constant here. It stay here in the B point. It doesn't change. So this is kind of transient state from one drop of water until the full water. The last drop of the gas, last bubble of the gas. This is the all stay in point B. So if you press harder, temperature and pressure doesn't change. So take place at the boundaries on the phase diagram here. Okay? And the system cannot move off these boundaries until the transition are completed. Transition completed means what? There's no bubble of air or there's no bubble of water vapor exists in this point. There's no air here, okay? There's only water vapor. And then there's no water vapor. I should say H2O vapor, okay? H2O vapor here at all. So it's here. And once you push it harder, and something happens. Okay? So the constant, so from the B to C is what? From B to C is constant temperature. If you increase the constant, temperature is constant, and you increase the pressure, this is always here. Okay? Always in the C point because there's no H2O vapor, so the pressure increase. Pressure increase from B to C. So if you increase the pressure, you push the piston harder and harder, pressure increase. Okay, and then what happened to C to D? C to D is that, okay, now, this is C point, right? You have pressure which is 760 millimeter mercury. And now you increase the temperature and make the pressure constant. Okay, then what happened? The constant pressure increase the temperature, and then increase the temperature, that means what? The first H2O gas will come out. Okay? Okay. So, and you will reach to D. You increase, if you increase the temperature, more liquid will become vapor. Increase more until all the water become vapor in the D point. We'll stay here. So this is C to D. Okay? And D is that even though you increase, I'm sorry, even though you increase the temperature, and if you stay here, you know that you have 100 Celsius, 760 meter mercury. It won't come out until all the vapor become, all the water become vapor, and you will move, the temperature will increase. So this is D to E. We are talking about C to D now. So take place at the boundary on the phase diagram. And the system cannot move off these boundaries until the transitions are completed. Okay? So from D to E, that means, from D to E means what? You already have all the vapors. So even though you increase the temperature and make the constants, this will become, the value will increase anyway. Okay, this is what we call phase transition process. So from A to B, B to C, C to D, D to E. You can use this diagram to explain what's going on in this process. Right. So we don't have time to introduce you 6.1b, estimation of vapor pressure. So the thing I just told you is important to know how to measure the vapor pressure in this process. And we have some equations, we have some charts for you to know how to measure, estimation of the vapor pressure. But unfortunately, we run out of our time today. I will talk about this on Wednesday.